And the initial seed of the random number generator isn't that bad. It's weird, but it's not that bad. So in the case of this, it's not that you wouldn't be able to predict where the random number generator starts. It's that you can enumerate all starting positions in a single lookup table. During a regular exchange, Alice knows Bob's static public key and ephemeral public key, as well as the certificate authority's certificate. All of the devices within a network will share a single certificate authority. So if you begin with one CA, it's very difficult to switch the network over to supporting 2. And all of the ephemeral keys come from the pseudo-random number generator, so you have 2 to the 16th power, about 65,000 total possible keys. If you're grabbing them from the same device repeatedly, you will only see 2 to the 15th, or half of those. And the shared secret is generated by a hashing function to create an AES key, which always looks random, because you wind up with the combined entropy of both Alice and Bob. So if you just dump the AES keys that are being used, you have 2 16-bit PRNGs being combined, plus 2 static keys, which are 190 bits random, being combined. And this all goes through a hash function at the end, so you wind up with random-looking AES keys. If you were just to audit that part, you would never notice this. The break itself came from Peter Ledbetter and Nigel Smart at ISC in 2003. The paper is entitled Analysis of the Insecurity of ECQMV with Partially Known Nonces. The conclusion of the paper is that they show it to be insecure for key sizes less than 2 to the 320th. That's 320 bits in elliptic curve style, which is, does anyone know? It's 3,000 bits by the RSA measure. In any case, they found this if the attacker is able to gain a small number of bits of each ephemeral key generated by his victim. In our case, we know all of them, every last bit, because we can generate a lookup table between them. And for a key length of 2 to the 160th, the 4 most significant bits were sufficient to recover the key. So I wanted this list of random numbers, and the documentation of the chip isn't sufficient to recreate the LFSR. Like, they don't include all of the taps and starting positions and things like that. So I just wrapped the library in C code, which is here on the left. I'll publish the slides so you can grab these from the blog article. Basically, all this does is it has a while loop that sets a flag as to whether or not it's ready to be harvested. And then the debugger single steps until the harvest pool is complete. Then it copies that pool out to the host, and it does the same thing over again. Here on the right, I have, so the left is C code running inside of one chip of the type that I'm trying to attack. Here on the right, I have Python code for the GoodFET. This runs on the host computer, and all it does is watch these same flags and perform the single stepping. Down here at the bottom is the GoodFET 11. This is the hardware that I used. Up here at the top, you can see a hex dump of the binary file, and I grepped for some bytes in the beginning. You can see how it's repeated every 8,000 hex, and it just shifts left by 1 byte because there is a single dead state that it never quite goes through. If the pool ever becomes 0, 0, sorry, 4 zeros in hex, it will get stuck there. So it avoids that naturally in its cycling. I have a dandy little portable application to demonstrate this. And I did a strange attractors graph. I'm not sure who first came up with this, but the idea is that if you just do a histogram of these bytes, it's flat. Like, they look statistically random. But if you do an XY scatter plot of successive bytes, where X is the first byte you sample, Y is the second byte you sample, you get these snowflake patterns. The same happens in 3D if you do XYZ. And this works for any random number generator based upon a linear feedback shift register. So this same thing has been used for port choices on operating systems. If you want to know whether a DNS port is guessable, you can dump the lot of them through packet sniffing and repeated queries, and then you can draw this graph to figure out how predictable they are. As far as the PRNG quality, 16 bits is a very short sequence. Only half of these are exercised within any given boot. So once you reboot it, it picks either the left set or the right set, and it never switches between those because it's sampling 2 pairs at a time and then throwing one of them out. This isn't exactly the same sequence as you would get from the LFSR alone, because even in the random number generator, they're throwing away things that might be random. The position is exposed by random backoff delays. So if this were the 1980s and you were doing this on a Commodore 64 and you couldn't afford to keep a 20 megabyte lookup table because you didn't want to waste your RAID array on it, you could instead figure out where it is within the random number generator by watching for random backoff delays. So you cause a packet collision through jamming, and you can hold that there until you release it. Then you measure the amount of time between you're releasing the jamming and the first packet being broadcast. That time is controlled by the last sample of the LFSR. And then you run through through the entire random number generator sequence until you find that time, and then you know exactly what's going to be used for the next key negotiation. None of this is necessary, of course, because 20 megabytes is now trivial. The random number generator itself was documented first in the ChipCon 1110, 2430, and older single chip devices. As I showed you in the earlier slides, the first devices were a radio which could be set next to a microcontroller. This is the second generation of chips, the first ones that contain a microcontroller on the same die. It's an Intel 8051 clone. So at first it was suggested just for collision avoidance and random delay, and for that it works splendidly. You can use 3 or 4 assembly instructions taking fewer than 10 cycles to get a number that's random enough to prevent accidental collisions. The problem came about with the ChipCon 2530, which is their most recent 8051 model. They've since switched to the Texas Instruments MSP430 core. Although they copied the bug over, and I'll get to that in a bit. So in the 2530 data sheet, they discovered that they needed a random number generator for cryptography. So as I imagine it, an engineer in Germany is handed informal documentation by the guy who actually designed the chip in Norway, and then he needs to call up some guy he's never met in Texas to explain how random number generators are supported by this chip. And instead of having to write software for it, he says, oh, we have a random number generator. It says in the data sheet, hardware random number generator. And it did. So he writes up this little paragraph. The random number generator uses a 16-bit LFSR to generate pseudo-random number generators, which is true, which can be read by the CPU or used directly by the command strobe processor, which is also true. There's a second little microcoded processor in this chip that you can use if you want to generate weird patterns for radio things, and you can sample it directly by that. So if you needed to scatter it or something, you might be able to do useful things with that. Then the last sentence is where it screws up. He says that it can be used to generate random keys for use in security. And this data sheet was read by all of the software developers who were making software for this. So if you grab the example code for this chip, both the standard libraries, it's called a hardware extraction library, or HAL. It's sort of the equivalent of the C standard library, but for hardware interaction. So it allows you to access the radio registers and things like that.